DeepSeek just built an AI that can simulate physics so accurately it's making traditional labs question why they even exist. And I'm not exaggerating. We're talking about a model that can predict molecular behavior, fluid dynamics, and particle interactions in ways that rival or outperform billion-dollar physics simulations. So what's actually happening under the hood, and why are research institutions genuinely nervous about this? Let me back up. For decades, simulating physics has been the domain of specialized software. You want to model how a drug molecule behaves in a cell? You run it through expensive molecular dynamics software that takes hours or days. You want to predict how air flows around a new airplane wing? You're looking at computational fluid dynamics, CFD, which requires massive computing clusters and PhDs who've spent years learning the math. These aren't casual tools. They're fortress-level gatekeepers. But here's where it gets wild. DeepSeek trained a model that learned physics patterns from massive amounts of scientific data, papers, simulations, experimental results, and it learned to compress those patterns into something that runs in seconds on a regular GPU. Not perfectly, not in every case, but often close enough to be genuinely useful. That's the shift. It's not that the AI is smarter than physics. It's that it learned to recognize the patterns that physics produces, and it can now generate predictions that match reality without solving the differential equations. Let me break down how this actually works, because it's less mystical than it sounds. Traditional physics simulators are rule-based. You feed in the initial conditions, particle positions, velocities, forces, and the computer applies the laws of physics step by step. Newton's second law, electromagnetism, thermodynamics. The math is bulletproof, but it's slow. For a complex system, you might simulate 5 seconds of real-world behavior, and it takes your computer an hour. DeepSeek's model is pattern-based. It was trained on billions of examples of here's the starting state, here's what happens next. The model learned to recognize the underlying patterns, how particles cluster, how energy dissipates, how systems evolve over time. It's not solving equations. It's learned to predict the outputs that equations would produce. And because it's a neural network, once it's trained, inference is blazingly fast. Milliseconds instead of hours. Now, here's the crucial part. It's not always accurate. There are edge cases, complex turbulence, extreme conditions, scenarios the model hasn't seen during training. Those are still risky. But for many real-world problems, drug design, materials science, climate modeling, protein folding, it's accurate enough to be a game changer. And crucially, it's accurate enough to be wrong in useful ways. You can use it to narrow down possibilities, to generate candidates for testing, to explore a design space that would have taken weeks to map manually. Why are labs panicking? 3 reasons. First, democratization. A researcher with a laptop can now do work that previously required institutional supercomputers and specialized software licenses costing tens of thousands per year. That's a power shift. Second, speed. If you can go from idea to simulation in seconds instead of days, you run more experiments, fail faster, iterate harder. The lab that adapts to this wins. Third, and maybe most important, nobody fully understands why it works as well as it does. Traditional physics is interpretable. You can point to the equations and explain the behavior. A neural network physics engine is a black box. You put in data, you get predictions out, and the path between them is millions of learned parameters that no human fully grasps. That scares people. It should. But here's the thing that's actually happening. This isn't replacing physics. It's augmenting it. The labs that are nervous aren't the ones adapting. They're the gatekeepers. The people who built their entire career and institution around being the only place with the computational resources or software licenses to run these simulations. That's changing. And fast. What DeepSeek did is prove that physics simulation can be treated like any other pattern recognition problem. You can learn it. You can compress it. You can make it cheap and accessible. And that's genuinely revolutionary for how science gets done. The real question isn't whether this works. It's how quickly labs adapt to a world where simulation is free and instant. Because the ones that don't will be left behind by the ones that do. If you want to actually understand what's happening in AI right now, not the hype, not the fear, just what's actually changing, subscribe. I break down one of these every few days.